All right, welcome back, everybody. Today we're going to be starting chapter 7, and the first section of that chapter is all about right triangle trigonometry. I'll go ahead and start the slides before I get too carried away here. So here we go. Uh, Here's what we're going to do. We're going to develop the theory of trigonometry using right triangle trigonometry. We're going to get a handy mnemonic to help us remember the relationships using right triangles. That's called SOHCAHTOA. Then we'll talk about the complementary angle theorem, talk about solving a triangle, and then we're going to do a few applications using right triangle trigonometry. All right, so the first thing I want to say is we developed the fundamental theory of trigonometry using the unit circle. And this was back in section 5.2. It was one of like the longer lectures right at the very beginning. Well, you can equivalently develop all of the theory that we've covered so far using right triangles. And we actually saw that a little bit back in that section. There were a couple of triangles that you needed to memorize, in particular the 30, 60, 90 triangles. Well, it turns out that you can extend that idea to any right triangle, and you can completely develop trigonometry from that perspective. So some of you might have done that back in like high school, for example. If not, that's totally fine. And one of the reasons that we like this book for this class is because it's really just better to develop it using the unit circle and then extend it to circles of radius r. And then later on, you can pepper in the right triangle approach, which is exactly what we're going to do right now. So if you remember section 5.2, we developed the theory using the unit circle. Then we extended it to a circle of any radius r. Where do I have? Yeah, any radius r right here. Uh, and now we're going to do all of this with right triangles instead. Either way, we can get the same results and we can recover the other developmental approach too, as we'll see in just a minute. So a quick review, a right triangle is a triangle that has a right angle in it. And recall that a right angle is just a 90-degree angle, or an angle that's pi over 2 radians. So a right triangle also has two legs and a hypotenuse. So you can always break down a right triangle into these three sides, two legs and a hypotenuse. So here's how we're going to do this. Start with a right triangle, and we're going to label one of the acute angles theta, right here. Then what we can do is we can refer to the legs of the right triangle as being opposite theta or adjacent to theta. And then we can also refer to the hypotenuse right there. You'll notice that I have these words underlined, or these letters underlined. So O, A, and H. We're going to see this in a couple slides here, but those are the letters that appear in that mnemonic SOHCAHTOA. But we'll get there in just a few minutes. So let's suppose that the lengths of our triangle, the lengths of the legs, I mean, are A and B. Let me highlight that right here, A and B. And the hypotenuse is C. Then we can define the trigonometric functions as follows. Here we go. So we're going to call sine of theta the length of the opposite leg divided by the length of the hypotenuse. So sine is opposite over hypotenuse. And we're going to define cosine to be the adjacent leg over the hypotenuse, the length of the adjacent leg divided by the length of the hypotenuse. And then tangent theta, we're going to define as the length of the opposite leg divided by the length of the adjacent leg. And there you go. So once you have those three, the other reciprocal functions are the same, you just reciprocate. So cosecant will be hypotenuse over opposite, secant will be hypotenuse over adjacent, and cotangent will be adjacent over opposite. And that's the idea. Let me dwell on this just a little bit. Let me erase some of this right here. Because what you want to do right triangle trigonometry is you want to start to get a picture of which legs you're referring to. So let's look at sine for a minute. So sine of theta, and let's look at this triangle down here. Sine of theta is opposite over hypotenuse. So it's going to be this leg divided by this hypotenuse right here. So that's sine of theta. There you go. And then if you do cosine theta, it's adjacent over hypotenuse. So you're going to divide those two lengths. And then if you do tangent, tangent is opposite over adjacent. There you go. So that's tangent right there. And then the reciprocals are all just the reciprocals. Flip everything and you get the reciprocal functions. So this is how we define these functions using right triangles instead of a unit circle or a circle of radius r. And how do you remember this? Well, there's a really, really handy mnemonic called SOHCAHTOA right here. SOHCAHTOA. So this is something that I recommend you memorize. It will help you remember what the definitions of these functions are. So what it stands for is this. It stands for sine is opposite over hypotenuse. So SOH, sine equals opposite over hypotenuse. Then CA stands for cosine equals adjacent over hypotenuse. So you've got CAH, cosine equals adjacent over hypotenuse. And then TOA is this one. Tangent is opposite over adjacent. And so that's how you can remember these. SOHCAHTOA, SOHCAHTOA, SOHCAHTOA. Say it, 100 times in your head, say it out loud. In fact, here, let me throw up the thinker and the speaker for a minute. So I just want you to say these out loud to yourself to help, memorize this mnemonic. All right, so now we can use this when we want. But what I want to do next is I want to see how this connects to the unit circle approach or the circle of radius r approach. So here's what we can do. If we take that angle theta and we put it in standard position on the Cartesian plane. So remember, standard position means you put the vertex at the origin. Well, if you do that, then the end point of the hypotenuse lies on a circle of radius c. And the equation of that circle is x squared plus y squared equals c squared. And this is exactly how we defined the trigonometric functions for a circle of radius c back in section 5.2. So this is the recovery of all that other theory that we've been talking about for the whole course. And again, you can see it's equivalent because there's essentially a one-to-one relationship between these triangles and the circles that they generate. So when you develop trigonometry, you can develop it from either direction you want. You can start with unit circle and circles of radius r, or you can start with a quote unquote unit triangle, which is really a triangle with a hypotenuse length 1, and then you can get the circles from that. So whichever way. But what I've noticed in my own experience and my own research is that oftentimes one interpretation is easier to use than another interpretation, but it really, really depends on the context. So there's no hard and fast rule that says you must do it this way, you must do it that way. But you're going to see this in play in the next section. So the next section we're going to cover is 6.2. And this is exactly why I delayed that section to be after this section, 7.1, because using the SOHCAHTOA interpretation makes 6.2 much easier, as you'll see. But we'll get to that. Okay, so let's try an example here. So let's find the exact value of all 6 of the trigonometric functions of the angle theta using this triangle right here. So think about it on your own for just a minute. Okay, now what I want you to do is I want you to say SOHCAHTOA out loud to yourself and what SOHCAHTOA represents. So what does that mnemonic actually stand for? All right, now you try this one on your own. See if you can come up with the value of all 6 of those trig functions using SOHCAHTOA, and then we'll do it together. All right, here we go. So I remember SOHCAHTOA stands for sine equals opposite over hypotenuse, cosine equals adjacent over hypotenuse, and TOA means tan equals opposite over adjacent. See, that's why you need the mnemonic. So if we want to know all of those values, if we want to know opposite over adjacent and adjacent over hypotenuse and opposite over hypotenuse, we need to know the length of all 3 sides of the triangle. But in this case, we actually don't know this length yet. So in order to get that, we're going to have to use the Pythagorean theorem. So remember, the Pythagorean theorem says this. a squared plus b squared equals c squared. So we're just going to fill in the information we know and solve for the information we don't know. Okay, so we know one of the legs and we know the hypotenuse. So we can fill that out here as 3 squared plus b squared equals 5 squared. And then we just do some basic algebra here to solve for b, which is 16. So b is going to be 4. Or really, I should say this. B is going to be plus or minus square root of 16, which is plus or minus 4. But in this case, because we're just using a positive length, we're just going to stick with the positive result. All right, so now we know that the length of that opposite side is 4. Okay, now the fun part. Since we know SOHCAHTOA, we can easily produce all 6 of the trig functions at a glance just by using that mnemonic. So sine of theta is opposite over hypotenuse, so it's 4/5. Cosine of theta is adjacent over hypotenuse, so it's going to be 3/5. And then tan theta is opposite over adjacent, so it's going to be 4/3. Done. Now we can find the reciprocal functions just by flipping everything. So cosecant theta is 5/4, secant theta is 5/3, and cotangent theta is 3/4, and we're done. Yay, right? SOHCAHTOA. Here is all the work there written out more cleanly, so if you want to refer to it, you can. Yeah, and that's basically the idea. So once we know SOHCAHTOA, we can do a lot pretty quickly. Okay, so now let's talk about the complementary angle theorem. So we say that two acute angles, are complementary if and only if their angles add up to 90 degrees. So that's what we mean by complementary. Notice that the spelling of this word complementary is different than like a compliment you would give someone. There's an E here instead of an I. So we are talking about complementary angles. And complementary means they add up to 90. So an important note here, because we're working with right triangles, we know one angle of the right triangle is already 90 degrees. And since we also know that the angles of a triangle must add up to 180 degrees, it follows that the two acute angles have to add up to 90 degrees on their own. So what that means is if you've got a right triangle here, this one's already 90 degrees. So that means that this one and this one have to add up to 90 degrees too. So those two angles are complementary. So that's the idea. The two angles of a right triangle, the two acute angles, are complementary angles. Okay, now there's an interesting connection here between these complementary angles, and this picture kind of details it. So let's focus on the angle B for now. Right? So if we focus on the angle B, then we can use SOHCAHTOA to figure out what sine and cosine and tangent are. So sine of B is going to be opposite over hypotenuse, right there. So that's the opposite over hypotenuse. But check this out. If we now switch, oops, wait, there we go. If we now switch our perspective to the angle A, well, if we look at the highlighted legs that we just highlighted, or the highlighted sides, we've got the one that's, sorry, here you go. We've got the one that's adjacent to A and the hypotenuse. So that means that that's the cosine of the angle A. So in other words, sine of B is equal to cosine of A, and that's what this result is showing right here. So it's kind of like if you look at the value of sine from one of the angles, it's going to be cosine of the other angle, and then vice versa. So that's what each one of these little cases goes through. Let me do this. So let's look at cosine of B for a minute here. Cosine of B, that's adjacent over hypotenuse, right? So that's this over this. But if we now shift our focus to the angle A, now we're looking at opposite over hypotenuse. But that's the sine, right? That's sine of A. So cosine of B, cosine of the angle B is equal to sine of the angle A. And so you get this relationship here. And that relationship holds for all 6 of the trigonometric functions, all 6 of them. So sine of B is cosine A, cosine B is sine A, my little highlighter, there it is, sine A, tangent of B is cotangent A, and then so on. So cosecant B is secant A, secant B is cosecant A, and cotangent B is tangent A. There we go. So you get all these really nice relationships that hold, and that's what leads us to the complementary angle theorem. So what's happening here is these functions are what we call co-functions of each other. That's one of the reasons that the word co appears, like cosine and cotangent and such, cosecant, for example. So the functions sine and cosine, tangent and cotangent, and secant and cosecant are called co-functions of each other, respectively. And the complementary angle theorem is pretty much what I was just pointing out on the previous slide, which is that co-functions of complementary angles are equal. So let's see an example here. For example, sine of 30 degrees is cosine of 60 degrees. Those two values are equal, they're the same. Or tangent of 20 degrees equals cotangent of 70 degrees. Those two values are equal because those are co-functions of one another. So how are we coming up with these results? Well, we're basically just looking at the difference between 90 degrees and the original angle. So here, let's look at this. So sine of 30 degrees, well, the complement to 30 degrees is 60 degrees. So sine of 30 degrees is cosine of 60. And then same thing down here. The complementary angle for 20 degrees is going to be 70 degrees because 20 plus 70 equals 90. And then now we've got this example here. What's sine of 5 pi over 12? Well, that's equal to cosine of pi over 2 minus 5 pi over 12, because that's the complement of 5 pi over 12. And when you do the arithmetic, you get pi over 12. So that tells us that sine of 5 pi over 12 is the same as cosine of pi over 12. In other words, those things are interchangeable. So those values are equal. So you can replace them anywhere you see them appear, which is kind of nice. All right, so that's SOHCAHTOA, that's the complementary angle theorem. Now let's talk about solving a triangle. So for the next several sections, we're going to be doing a lot of this process, solving a triangle. So what does it mean? Solving a triangle means to find the lengths of all three sides of a triangle and the angle measures of all three angles. So in essence, you're completely solving the triangle. You're finding all the lengths of the legs and all the measures of the angles. And once you have all of that, the triangle is solved. So there's some interesting questions that go along with this process, like if we know some information about a triangle, can we solve it? So if we're given some information, can we actually solve it? Can we find the missing information? Another interesting question is, what's the minimum amount of information that we need to solve a triangle? Minimum amount of information that we need. And this is something we'll explore more in sections 7.2 and 7.3. But yeah, that's kind of the idea. So we're going to explore these here and in the next two sections of chapter 7. And we're going to start with right triangles now. And then in 7.2 and 3, that's when we extend it to non-right triangles. All right, so let's try this example. And I want you to think about this one and try it on your own too, but let's read it out loud together. Here's a triangle. If B is equal to 4, if B is equal to 4 and A is equal to 35 degrees, solve the triangle pictured. Oops, it's kind of hard to see that 35. Here we go. Oops, there we go. So you know a side length, and you know the angle A is 35 degrees, and you know the right angle is 90 degrees. So what I want you to do is think out loud how you would, or think about how you would start this problem first. All right, now say something out loud to yourself about what you're going to need or what you're going to use to solve this triangle. All right, now try to solve it on your own. See if you can find all of the angles and all of the lengths. Okay, and now let's do it together. Just for the sake of time, I'm going to use my slides instead of writing everything out, but here's how we can proceed. We know that A and B are complementary angles. And in fact, let me rewrite this right here. So this is 35 degrees. So if they're complementary angles, that means that B has to be 55 degrees, just like so. So now we know all three angles already. So we know A, we know B, and the third angle is 90 degrees. Now, we also know that this length B is 4, so now we need to find A and C. And how we do this is essentially we want to find something that relates a side that we know with the side that we don't know. That's basically the idea, and we're going to see more of this in the next examples. So for example, if we wanted to solve for the side A, well, what we want to use is we want to use a trig function that relates the side we know, length 4, and the side that we're looking for, length A. So what function relates an angle that is that is adjacent to A and opposite A, for example? And then you can quickly realize that it's going to be tangent, right? So opposite over adjacent, that's tangent. So we know that A is 35 degrees. So we know that tangent of that angle has got to be little a divided by 4, opposite over adjacent. And then at this point, you can do some basic arithmetic, and then you can get an approximation of what this length is going to be. So if tangent 35 degrees is a over 4, then we know that a is equal to 4 times tangent 35 degrees. Then you can go to a calculator, and the calculator will give you this approximation, 2.8008. Real quick before we go to the next little piece here where we do sine of 55, if you're using your graphing calculator for this, or even just using any computational resource, you got to make sure that you're in degree mode. So generally speaking, the default is radian mode because radians are just more robust than degrees. So if you're doing this with your calculator, scientific calculator, graphing calculator, make sure that you are in the degree mode when you're using degrees. Usually you can find that if you click the mode button on your calculator, there's usually a mode button, and just verify that you're in the right mode for angles. Another thing I want to point out is this, because this is something that's really important that I emphasize in all of my classes. This is the equality. So what we know is that length is equal to 4 tangent 35 degrees. But tangent of 35 degrees is an irrational number. So that means that the simplest way of writing it is basically already here. That's about as simple as it gets. 4 tangent 35 degrees. Whatever that length is, whatever that real number is, it's that. That's what it is. And we can picture it. It's this length right here. That's what the length is. So when I evaluate that in my calculator is not giving me an exact value at all. My calculator is giving me an approximation. And so you really do want to be careful with this because when you take an approximation, you're introducing an error to your computations. So general rule is this, and you should take this as long as you possibly can. Never approximate anything unless somebody actually forces you to approximate it. All right? So you should always try to leave everything exact until the very, very last minute. Because what you don't want to do is you don't want to round or approximate early on and then use that result for more calculations down the line. Because if you do that, then you're going to be carrying this error with you, and the error might compound as you go along. And it might compound so much that your final answer is not valid anymore because the error has grown so large. So generally speaking, don't approximate unless you are asked to. Keep everything exact. And if you really, 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 really need to, then approximate. Okay, so that's my spiel about that. Let's look at the other angle. So the same idea. Let me clear this, right? So we also want to know, hold on a sec. So we know what A is now. A is approximately 2.8008. Now we need to know what C is. So how do we find C? Well, our choice. We want to find something that we could relate the adjacent leg to A and the hypotenuse, or we could do the adjacent leg to B. Oh, wait, hold on. Oh, no, I'm sorry. We could do the opposite leg of B in the hypotenuse, which is right here. Oops. Oh, yeah, there we go. That's what we're doing. So remember, sine is opposite over hypotenuse, so it's going to be 4 over C. Once we know that sine of 55 degrees is 4 over C, we can solve for C simply by basically multiplying and dividing, or you can do a flip and multiply, and we'll get that C is equal to 4 over sine of 55 degrees. Plug that into a calculator, it will give you the approximation 4.8830. So now we know all of the information about the triangle. We've solved it. Oops. 4.8830. All right, now the triangle is solved. We know all 3 angles, we know all 3 legs. Solved. Okay. All right, now let's move on to some applications. So this is a lot of where, well, a lot of where right triangle trigonometry gets used is in applications. So maybe this is the type of thing that you can now think about when you're walking around outside, or if you ever see a surveyor, or if you ever see or wonder what those machines are doing, they're doing a lot of right triangle trigonometry. So let's look at this example. A surveyor can measure the width of a river by setting up a transit at a point C on one side of the river and taking a sighting of a point A on the other side of a river. So a transit is actually that machine that you see surveyors using, where it's like on a tripod with 3 legs, and there's like almost like a giant camera box on it, and they're usually pointing it at somebody who's way down the line, way down the street, and at the other end of the street they've got a pole with a little reflector on it. So that's what's going on here. Basically, you set up at the point C, aim the transit at the point A, and then that's how this is going to work. That's how this is going to work. So then what the surveyor does is they turn 90 degrees. Hold on, lost my spot in the reading. Oh, yeah. So turn through an angle of 90 degrees the point C, and then the surveyor walks a distance of 300 meters. Then what they do is they're going to turn the transit and point it at point A again. Oop, can't really see that. They're going to point it at point A again. And what they'll realize is that the angle that they had to turn was 30 degrees. So they measured that angle, they found it to be 30 degrees. So now the question is, how wide is the river at the point C? Or I should say, how wide is the river between C and A? How could we find that out? So think about this one on your own for a minute, and then we'll do it. How would you find that length over there, the length B? Okay, let's do it together. So you can always phrase it in these terms. We know information about the side adjacent to theta. We know this information here. We want to know information about the side that's opposite theta over here. So what is a function that relates the side adjacent to theta and the side opposite theta? And if you remember SOHCAHTOA, you're talking about adjacent and opposite, so you're thinking of tangent. That's what it should be. So we know that tangent of theta is opposite over adjacent, so it's going to be B over A. But we know what A is. A is 300. There we go. And we actually, we know what tangent of 30 is too. We know what tangent of 30 is as well, because 30 is one of those standard angles. See, I should have included the exact value here. I only included the approximation. But once we know this relationship, we can solve for B, and we get that B is equal to 300 tan 30. Plug that into a calculator, and you'll get 173.2050 meters, approximately. But I'm curious, let's see if we can add this little bit to it. What is tangent of 30? Well, tangent is, what is it? Tangent is sine over cosine, right? Well, I think we're going to need more information actually, because I just remembered we're not working on a unit circle, huh? We're not working on a unit circle, so we can't go straight to that amount. All right, I take it back. We're stuck with this. So 300 tan 30, 30 degrees, plug that into your calculator, get an approximation. Okay, next example. There's a statue mounted on the top of a building. Oops, right over here. There we go. Now from street level, two observations are taken, 500 feet from the center of the building. So this length is 500 feet. Now the angle of elevation to the base of the statue is measured to be 43.2 degrees, and the angle of elevation measured to the top of the statue is 46.1 degrees. So what's the height of the statue? That's what we want to figure out. The angle of elevation is just the angle that is swept out from this baseline up to whichever line you're interested in here, whichever hypotenuse. That's the idea. So that's the angle of elevation. You can also talk about an angle of declination, which is basically going down instead. But the idea is the same. You're going to sweep out some angle. So think about this one on your own for a minute, and then we'll do it together. How would you find the height of the statue? All right, now say something out loud to yourself. What would you use? What's something that you think could help you find the answer to this question? All right, now let's try it together. So first thing I'm thinking here is we've got two angle measurements, so we're probably going to need two triangles. But we're also definitely going to be using a right triangle. So here, what I see in my head is I see a right triangle being formed right here and right here. But there's going to be two of them because we have two different angles theta, if we call that angle theta there. So here we go. Use two right triangles, one with a vertex at the top of the statue. This would be like the top. And then one with a vertex at the base of the statue. This would be the base. Oops, let me write that a little nicer. Base. Right? So B prime is the distance from the ground to the top of the statue, and B is the distance from the ground to the base of the statue. Here's our two angles theta, 46.1 degrees and 43.2 degrees. And what are we trying to figure out? We need to know what B prime and B are if we want to be able to find the height of the statue. What do we know? We know this length is 500 in both cases. So we need a function that's going to relate the angle adjacent and the angle, or sorry, we need a function that's going to relate the leg that's adjacent to the angle and the leg that's opposite the angle. Adjacent and opposite, opposite and adjacent, that's tangent, right? So we're going to use tangent again. So we know that tangent of 46.1 degrees is going to be opposite over adjacent. And with that information, we can solve for B, use a calculator to get an approximation, and we get this. Sorry, solve for B prime. Then we repeat the argument. So tangent of 43.2 degrees is going to be opposite over adjacent. And now we have that. We can solve for B and get an approximation with a calculator. So now we know B prime and we know B. So if we take their difference, we'll get the height of the statue. So the height of the statue is B prime minus B, which comes out to about 50.0456 feet. Nice. Not too bad, right? SOHCAHTOA, relating the sides of the triangle, it just makes things nice and clean. SOHCAHTOA. Okay, let's do one more example now. This one is all about bearings, which are pretty interesting, and some of you might actually really use these in the future. So when you're doing navigation or when you're surveying, the direction or bearing from a point O to a point P is defined as the acute angle between the ray OP and the vertical line passing through O, the north-south line. So in essence, you've got a north-south line, and then you've got some ray that you're on, or some ray that's giving you a direction, right? Well, the bearing is basically whatever this acute angle is in between that north-south line and your ray. That's what it is. So that acute angle. And then we also use the symbols north, south, east, and west to indicate what quadrant we're in. So let me look at this figure in a little more detail. Let's focus on this ray first. The ray that passes through the point P1. So the angle between the ray OP1 and the north-south line is 30 degrees. Oops, is 30 degrees. Come here, there we go. 30 degrees. So the way that we describe that bearing, the bearing that goes along the ray OP1, is north 30 degrees east. North 30 degrees east. So the north, the N and the E, the north and the east thing, those letters tell you what quadrant you're in. You're in the northeast quadrant. Down here, you would be in the southeast quadrant. Over here, you would be in the southwest quadrant. And over here, you would be in the northwest quadrant. So what you do when you're using bearings is you basically talk about the angle that you sweep out from the north-south line to the ray, and then you say what quadrant you're in. So let's look at the point P2. Here we go. Here's this ray. All right, so the angle, the acute angle that this ray makes with the north-south line is 50 degrees, just like so. And since we're in that quadrant, the third quadrant, we're going to say that the bearing is south 50 degrees west. And that's the idea. That's the idea. Let's try to do this one. I'll let you think about this one and then we can answer it together. Let's look at the ray that passes through the point P4. All right, so try this one on your own. Think about it and say it out loud. What is the bearing for that ray OP4? Okay, well, let's look. The angle is going to be 20 degrees, and because we're in the southeast quadrant, the bearing is going to be south 20 degrees east. So we would write it like so. South 20 degrees east. And that's the bearing for that ray, OP4. Okay, now let's try an example. So let's say a Boeing 777 aircraft takes off from Nashville International Airport on runway 2 left, and it has a bearing of north 20 degrees east. And then after flying for 1 mile, so it goes this way for 1 mile, the pilot turns 90 degrees and then heads toward the northwest quadrant. So the request to do so is granted, and then the plane goes 2 miles in this direction. So now the question is, after the plane goes 2 miles in that direction, what is the bearing that the control tower should use to locate the aircraft? So what is this bearing right here? Kind of messy. Let me erase this and this. There we go. What's the bearing of that ray right here? Oops, I just erased it. That bearing. All right, so think about that one on your own. Think about how you would approach it first. All right, now say something out loud to yourself, maybe like a first step you would take. What would you do? All right, now try to work it out on your own. See if you can come up with the bearing, and then we'll do it together. All right, here we go. So in order to find the bearing, we first need to find this angle theta as it's pictured here in the figure. So we need to know this angle theta. If we can figure out that angle theta, then we can figure out what this angle is right here. This angle right here that I'm sketching in blue. So that's the angle that we need to know to be able to define the bearing. To find that angle, we need to know the angle theta, and then we need to subtract, because we know that this angle here is 20 degrees. So how do we find angle theta? Well, what information do we know? We know information about the side that is adjacent and opposite that angle theta. Adjacent, opposite, opposite, adjacent, that's tangent, right? That's tangent. So if we use the tangent function, we can find what that angle theta is. And that's exactly what this calculation is showing down here. So we know that tangent is opposite over adjacent. So it's going to be 2 over 1. And then at that point, we need to solve for theta. And the way that we solve for theta is we use the arctangent function. Arctangent function. And we would do arctangent of 2. So again, remember when you're working with your calculator, you need to be sure that you're in the right mode, right? So here we're working with degrees, So we need to be in degree mode. And if we put our calculator in degree mode and we compute tangent inverse of 2, it'll approximate that value as 63.4349. So that's the angle theta. Let me just emphasize what's going on here. That is the angle theta right here, the whole angle. Now we need to know what our bearing is. So we need to take that angle and subtract 20 degrees, which is exactly what we're going to do. So we take our angle and we subtract 20 degrees and we get this as an approximate bearing. Since we're headed to the northwest quadrant, our bearing is going to be north 43.439 degrees west. And that is the bearing. All right, so that's it. Let's play. You should go try to do the homework. Remember, you can ask questions on Canvas if you'd like. You can email me as well. But that's pretty much it. So the main takeaway from this is now we have right triangle trigonometry. And that example we did at the end is actually one of the reasons that I wanted to wait until we cover section 6.2. Because now we're going to go and we're going to cover section 6.2, which is more about inverse trig functions. But what you're going to find is it's actually easier to evaluate these inverse trig functions when you use the right triangle interpretation, because you can always just think of SOHCAHTOA and you can create a right triangle. You just have to orient the right triangle in the right way, and then you can just read the information off the triangle. So that's what we're going to do next. So I'll stop rambling and I'll see you all next time.